So in the previous video we were looking at this example matrix, which is just sort of some randomly generated matrix I got from your homework, and these were the eigenvectors and eigenvalues which helped us describe what the matrix does. But I sort of skipped from having the matrix to just having these. I just pulled the answer from your homework answer system. So in this video, let's look at how to actually get the answer. So how do we solve an eigenvalue problem? And here's, I guess what I've written here is a good description of what the eigenvalue problem is. So given a matrix A, it doesn't have to be 2 by 2, it could be any square matrix, so n by n. So given an n by n matrix A, we'd like to know its eigenvectors and eigenvalues. What that means is we'd like to know some non-zero vectors v and some numbers, lambda, so that AV is lambda v. So think of it as solving an equation, but it's kind of a weird equation. It's an equation where this is known. The vector showing up is unknown. We're trying to solve for that. And the scalar here is also unknown. So this is kind of weird. Often we have equations with a family of unknown scalars or equations with a family of unknown vectors. But here we have kind of this mixed weird situation. So we first ask okay, so first of all, when I say solve this equation, I'm not suggesting that there's a unique solution. So like we saw here, there are two solutions, right? Actually, there are infinitely many solutions. But there are two solutions if you want the vectors from your solutions to be linearly independent. So we got this one and this one. And here, there are these two solutions. Really, there's infinitely many because you can double or triple or scale this vector by any factor you want and it will still be a vector, eigenvector with eigenvalue 2. So actually, there's infinitely many solutions. So I'm not saying there's a unique solution. When I say solve, I mean we want to find all possible solutions, pretty much. Now, the way we're going to address this is first we're going to focus on lambda and ask for what numbers lambda could there possibly be a v that makes this work? For what numbers lambda could there possibly be a v that makes this work? And here's a way to get at the answer to this question. So first subtract lambda v from both sides. Then view it like this. So what I've done here, I here stands for the identity matrix. So it's a matrix that does nothing. I think I didn't mention this in the previous linear algebra lecture, but it showed up in your homework. It's a matrix that does nothing. So like if we're talking 2 by 2, it looks like this. This is a way of describing the operation of just scaling as a matrix. So like here in the second term, lambda times v is the same as if I took this matrix, lambda times identity, and applied it to v, right? This matrix would be lambda 0, 0, lambda, and then when you apply that to v, that's the same as just scaling by lambda. And we're interested in non-zero v's, right? So we're purely interested in non-zero v's. Now, there's only possibly a non-zero v that makes this true. That can only possibly happen if this matrix has a non-trivial null space, right? We're actually interested in v's that are in the null space of this. So actually, let's write it down like this. We have another description of how eigenvectors and eigenvalues work, or what they are. Instead of saying an eigenvector is just something that gets scaled by the matrix, we could say this. An eigenvector with eigenvalue lambda, we could have just defined, actually, it's just the same thing. It's just any non-zero vector that is in the null space of A minus lambda identity. So take this matrix, A minus lambda identity. The non-zero vectors in its null space are exactly what we mean by eigenvector with eigenvalue lambda. So when does the choice of scalar lambda have associated eigenvectors. When are there associated eigenvectors? So I'm going to say there are non-zero v's to go with this. Eigenvectors have to be not zero. There are non-zero v's to go with this when null space of this is non-trivial. And when is the null space of this thing non-trivial? When its determinant is 0, right? That's a good way of getting at, that's a good criterion for when the null space is non-trivial. So, i.e., when the determinant of this matrix is 0. And just like that, we've gotten rid of the v. Right here we had an equation with two unknowns, an unknown vector and an unknown scalar. And now I've got an equation with only one unknown thing, the scalar lambda. So this is one equation, one unknown. So in principle, this should be something that has hope of being solved for lambda, right? Now this will actually be a polynomial. So if A is like a 10 by 10 matrix, then this will be a degree 10 polynomial. This will be some polynomial. So it'll have some roots. If A is a 2 by 2 matrix, it'll be a quadratic polynomial. So it could have up to 2 roots. It might have no roots, and it might have repeated roots. So we get this split into 3 possible cases that we're kind of familiar with now. So this is a polynomial in lambda. And only for the lambda equals roots of this polynomial, only when lambda solves this polynomial, do we get non-zero v's existing. And that pretty much sums it up. If you already know how to solve linear systems, if you already know how to solve linear equations, then this information, that's the only tricky part, is just figuring out that this is what you need to do. And from here you can solve eigenvalue problems. But let's just do an explicit example with this one to, I guess, solidify the idea. So, oh, by the way, I really only commented on how to get the lambdas, but how do you get the associated v's? I sort of stopped there because I'm assuming you already know how to solve linear systems. So if you find a particular lambda that works, then what are the associated v's? They're just the vectors in the null space of that matrix. And we've already gone over how to find the vectors in a null space. Okay, so let's just do it to this, and I think it'll become clear. So hopefully when we do it, we'll get this answer. What was it? 0, -3, 2, 5. Okay, so first we find the eigenvalues. So the possible eigenvalues are the ones that solve this. So the first thing we want is the solutions to this equation. So let's see, 0 equals, so here's the equation. 0 equals the determinant of, and then I'll write down the matrix, 0, -3, 2, 5, minus, and then lambda identity, that's just a matrix with lambdas down the diagonal. So in other words, we're looking at determinant of 0 minus lambda, so minus lambda, -3, 2, and then 5 minus lambda. So that's, so it's that. Let's see, then there's some steps to simplify, and there are a million places where I could have made a minus sign error. So make sure you write neatly and keep track of your minus signs. Don't skip too many steps when you do this. Or I'll show you something you can do in Mathematica to maybe check your work, or just skip over some of this stuff here. So this is a quadratic polynomial, so I want to write it like that. Let's see, negative. Okay, and combine all the terms and stuff. This one is simpler than usual, I guess. So there's not too much algebra going on here. Okay, now I just want to factor this and I barely even have to think because I've cheated and I already know the answer is 2, 3. So is this lambda minus 2 times lambda minus 3? Indeed it is. This polynomial does factor that way. So now you see where these special magical scale factors are coming from. They're the roots of this polynomial. That's where the 2, 3 came from. So that tells us that there are two eigenvalues for this matrix. Lambda equals 2 and lambda equals 3. Two eigenvalues. And each eigenvalue is going to lead to its own collection of eigenvectors. Here, just one eigenvector for each is what I want in the end, but each eigenvalue could lead to a collection of eigenvectors. I mean, actually, it is leading to a collection. I'm just representing that collection by one vector. Really, with the eigenvalue 2, any scalar multiple of this vector would also work equally well as an eigenvector, right? Except for 0. So now, so it's kind of like two steps, right? So step 1, find the solutions to this. We have found the eigenvalues. Now for each eigenvalue, find the associated eigenvectors. And I'm putting a dividing line here to emphasize that each eigenvalue will have associated eigenvectors. It's not just these two disorganized lists. These are the eigenvalues, these are the eigenvectors. No, the eigenvalue goes with an eigenvector each time. So what are the eigenvectors for eigenvalue 2? Well, they're the vectors that are in the null space of A minus 2 times the identity, right? So 2, 0, 0, 2. So what I want is the null space of this. Those would be the eigenvectors. So what is this matrix? Let's see, 0, minus 3, 2, 5. Then I just want to subtract 2 from the diagonal. So negative 2, minus 3, 2, and then 5 minus 2 is 3. So it's this. What I want is the null space of this. The null space of this will just be a line, right? It'll be a line through the origin. And all I want is one vector on that line. So when I write down the equation, this matrix xy equals 0, 0, it looks like two equations, but it's really one equation, right? Not a big surprise, right? You're not surprised to see that the second row here is a scalar multiple of the first row, because lambda equals 2 was rigged to make that happen in the first place, right? The fact that we subtracted 2 off the diagonal here was a consequence of wanting to make the determinant of this 0, right? So no surprise that one row is a multiple of the other row. So you only need one of the equations. So let's say I take 2x plus 3y equals 0. The other equation is just a repeat, pretty much, of the same equation. And then I don't know, whatever is your favorite way of writing down or expressing the solution. So if you want to express all solutions, then you can solve for one variable and treat that as sort of your a free parameter. So I could be like, maybe solve for y. Y is negative 2/3 x. So any vector whose second component is negative 2/3 of the first component is going to work as an eigenvector. So then any multiple of 0, negative 2/3, sorry, 1, negative 2/3 will work as an eigenvector. So here x could be anything. Usually, I mean, we just want to give one eigenvector in the end, and that's enough. So I can just pick any number, not 0, for x, and how about I pick x equals 3 just to clear out the denominator. So 3, negative 2 is an example of an eigenvector. So from lambda equals 2, we examined the null space of A minus 2 times the identity, and we found this non-zero vector in there, 3, negative 2. And is that what we had? Well, we had -3, 2, but that's just a scalar multiple, right? So we also, if I chose x equals -1, if I chose x equals -3 here rather than x equals 3, I would have gotten -3, 2. And then for lambda equals 3, we do a similar thing. So let me just do that off screen. Okay, so I'm subtracting 3 times the identity, and then I'm interested in this. And then, oh wow, one equation is a scalar multiple of the other, and I'm not surprised because that's something I made happen. And it looks like it comes down to basically x, 2x plus 2y is 0, which is the same as x plus y is 0, which is the same as saying, any scalar multiple of 1, -1 is going to work for that. So 1, -1 or -1, 1. So that's where the other eigenvector came from. All right, so step 1, find the solutions to this to get the eigenvalues. And then step 2, for each solution you got, which you could get none, actually, we have to discuss that. But assuming this step worked and you got, for a 2x2 matrix, assuming you got 2 solutions, then for each solution you got, find out what is the null space, find at least one non-zero thing in the null space of A minus that solution times the identity. Now, okay, here's where I was describing the technique. From AV equals lambda V, we go and see that in order for there to be non-zero V's that make this true, A minus lambda I has to be a singular matrix, a matrix with non-trivial null space, also known as a matrix with determinant 0. And when you write this equation down, you get a polynomial in lambda, just like we did over here in this example, right? We got a polynomial in lambda. But let's say you get a quadratic polynomial in lambda if you're doing a 2x2 matrix. You could get repeated roots, you could get 2 distinct roots, you could get no real roots. Those are different situations that need to be examined sometimes separately. So let's look at some of those in the next video.